this might be dangerous, but I'm going to do it anyway. So I'm going to show you a demo here, and we're going to do the chapter summary for electromagnetic induction. Now I'm going to show you a few demos, but I'll probably make another video with more detailed demos. Yeah, so let's just get to it. So let's see what I have right here. I'm going to hold it over with my right hand. And if I drop this, you're just going to make fun of me. Okay, there we go. So this is a coil of wire and a galvanometer. So the galvanometer measures really small currents. And I have here a magnet. Okay, so what happens when I put the magnet in the coil? Watch the needle as I put the magnet in the coil. So I got a current. But notice that if I just hold the magnet there, there's no current. It's only when I change the magnetic field in the loop of coil do I get a current. So in, I get a current, and when I take it out, I get a current. I could also take the magnet and rotate it. I can flip it over. And that would produce a current. So what we see here is a new way to make electric current, but really an EMF, an electromotive force. And that's with a changing magnetic field. Okay, so let me show you one more demo. Here's another way that we can make a changing magnetic field to make an electric current. So this is a hand crank generator. I have here a light bulb and my generator. And what I can do, well, I need to turn around this way, I guess. So I'm going to turn the hand crank generator. And I want to point this out because it's super important and it comes up in a lot of things in the real world. I use electricity. You probably use electricity. I suspect you're using it right now. We can hand crank and turn a coil of wire and a magnet. Inside there, that's just a motor. If you take a motor and a DC motor, there's a lot of different kinds of motors. If you take a DC motor and you spin the shaft, you can get an EMF out of the ends instead of the other way where you run current through it and you get this thing to spin. If I hook this up to battery, it will spin. The shaft will spin. But I want to point this out because, you know, I'm not going to sit here and turn a crank and make electricity for you. Okay. But I could get something else to turn this crank. One thing I could do to turn this crank would be steam. If I take some water and I heat it up, it turns into steam, and I have this turbine up here. The steam turns the turbine turns the generator, and then you get current. And then the question is, well, how do you make that steam? Well, the traditional way is to take a fossil fuel like coal or natural gas and burn it and heat up the water and make steam. That's not good because then you produce carbon dioxide into the atmosphere too, and we know that's a problem. Another way to make steam to turn this turbine would be with a nuclear reaction. So you can take a large mass like uranium and break it into pieces, and you get a lot of energy from that. You can use that energy to heat up the water and turn the turbine. So a nuclear power plant and a gas or coal plant are pretty much the same except for how they heat up the water. Now you could attach some blades over here and have the wind passing through it and turn it, and that would be like a wind turbine, a wind generator. Same thing, right? You could also make a dam and have water and have the water coming down, and as the water comes down, it turns that. So there's a lot of different ways that we can make power, and a lot of them use the same thing. If you have a hybrid car, then you have a gasoline engine that turns this and that charges the battery. So now there are some other ones that don't do this, primarily solar panels. There is a solar method that does do this, but a solar panel doesn't do this. And there's another one, a thermoelectric generator, but you know, this is something that's common. Okay. So let's talk about what's important here, and that's magnetic flux. So we're going to talk about flux, and in particular magnetic flux. So we use the symbol phi for that, and it's going to be equal to, let me go ahead and tell you the formula, and then I'll explain it to you. B A cosine theta. So imagine that I need a sheet of paper. Imagine that I don't want to talk about magnetic flux. I want to talk about rain flux, because rain flux is a little bit easier to understand. Rain flux would be how much rain hits this piece of paper. That's my rain flux. And you can see that how much rain hits the paper depends on three things: how hard it's raining, the size of the paper, but also the orientation of the paper with respect to the rain. If I rotate the paper like this and the rain's coming straight down, it's not going to hit the paper at all. So it depends on those three things. Magnetic flux depends on three things also. It depends on the area of the object that you're considering. It depends on the orientation and the magnetic field. So this is like the rain, and that's the area, and that's the angle. Now, let me just draw a picture. Suppose I have a magnetic field going this way, and then I have a surface like this. So it's looking at it from the side. That's my area A, and that's my magnetic field B. Theta is the angle between a normal to that line and B. So that would be theta right there, okay? So if I rotate so that the board is completely perpendicular to the magnetic field, theta would be 0, and the cosine of 0 is 1. Yeah, I had to think for a second there. Okay, so that angle is measured from the normal to that plane, not the plane itself. That's something that can be confusing. So now let's just jump to, once we know flux, we can jump into Faraday's law and Lenz's law, which gets a little bit complicated. So the first thing is, let's just redefine flux, B, A, cosine theta. Faraday's law says that, and we saw this, that you can make electromotive force a potential difference by changing the magnetic flux. And this is what that looks like. So if I have a bunch of loops, right, each one of those loops is going to have the same magnetic flux. So this N is the number of loops or turns. And then that's the magnetic flux, change in flux. Oh, I forgot to say flux capacitor. Back to the Future. I mean, so, Back to the Future, the flux capacitor, I don't really know what it is because that's a science fiction show. But this is what they do in science fiction. They say, oh, that's a cool word, let's use that. And it doesn't really matter if we use it the right way or not, but that's flux. Okay. And we do have flux in other situations too. And then T is the change in time. So this is the rate of change of flux. Now, this negative sign is a little weird in this equation, but everyone puts this in there. I wouldn't even put it in there. This is Lenz's law, and I'll explain that in just a second. Okay, so Faraday's law says that the EMF around a loop is equal to the number of loops times how fast the magnetic flux changes. So how do you change the magnetic flux? Well, I could change the magnetic field. I could change the area. You could take an area like this and squish it, or you could change the angle. So I could take an area and rotate it, and that would change the angle between those. Or you could do all those. Okay, so that's how we change the magnetic flux and produce an EMF. So when I take that coil and I put the magnet in there, I'm increasing the magnetic field. I'm changing that. That changes the flux. I get an EMF. Now, you only get a current, right, if you have a closed loop. So if the loop is connected to something, if it's just open, there's still an EMF produced, but you may not get a current. Okay, let's talk about Lenz's law. This one's really hard to wrap your mind around, okay? So let me just erase that stuff right here. And imagine that I have a loop of wire. And I have a magnetic field. And remember that X means it's going into the board. Now, after some short amount of time, I turn off the magnetic field. Now there's no magnetic field. So I'll go from magnetic field to no magnetic field. There is a change in magnetic flux, so there is an EMF induced around that loop. So I have an EMF. Now the question is, if I make a current, what direction is the current? And that's Lenz's law. Okay. So Lenz's law says that the current induced opposes, this is complicated, the change in flux. So if I make a current here, let's just say I make a current and it's that way. That current also makes a magnetic field, right? So which direction does that current make a magnetic field? In this case, that would make a magnetic field, a B induced coming out of the board. So the key here is that the current makes a magnetic field, and that magnetic field opposes the change in flux. So in this case, the flux is into the board and then nothing, and this wants to say, hey, no, don't change. So it would want to make a flux. This is going from into the board to nothing, so it's changing this way. So this wants to be in the opposite direction. So this actually wants to make a magnetic field going into the board, and it would be induced that way. Okay, so it wants to stop things from changing. It wants to oppose the change. That's what Lenz's law said. That's what that minus sign is there for. And that's what it means. If you calculate stuff for that, it doesn't always make sense because it depends on which way you calculate your EMF. So I don't like the negative sign there. It's important to determine that direction, but that's where it comes from. Okay. Let's go back and use Faraday's law to show something that we already showed. So in a previous chapter, we had this situation. So there's a wire and a movable bar, and it has a velocity v, and this has a length of I'm going to use lowercase l. And we said that the force on the charges in the wire are going to push them such that we get, in this case, let me get my the positive charges would have, remember the right-hand rule, QV that way, B is that way, so I'd get positives up here, negatives down there, and that would produce an electric field, and so the EMF induced would be, and I did this already, I'm not going to go through the whole thing, B, L, V, and that would be positive, and so you'd actually get a current. So pulling this through the magnetic field, you get a current. We can actually describe the exact same thing with Faraday's law. So let's imagine that I calculate the flux. So I want to calculate the EMF with Faraday's law. I only have one loop, so I'm going to use the positive version. It's just going to be the change in flux with respect to time. Well, I do have flux, right? Because I have all this area. Right. And so I can say this is going to be equal to the magnetic field B. The cosine of theta is 0 in this case because the perpendicular to the area is that way, and that's the same direction as the magnetic field. So I have B times the area, and let's say this is W, let's just call this X. Let's call that X, and times L. So this is X times L. That's my flux. But I need to change, that's not right. That's what I'm going to find. But let's just say I have the flux. It's B times X times L. That's my flux. Okay. Now suppose that after a short amount of time, it's moved the bar over here an amount delta X. Well, if I go from here to there, I can write my change in flux as this flux, which is going to be B X plus delta X times L, right? Because it got a little bit bigger. And then minus the initial flux, BXL. So if I multiply this out, I get B delta XL, right? Because the BXL minus BXL cancels. Now let's calculate the EMF. It's going to be equal to the change in flux, B delta XL, divided by the change in time. But look here, if I have delta X over delta T, that's the velocity. So this is B L V. It's the same thing. So we can explain the same thing using this motional EMF from the previous chapter or Faraday's law. Eddy currents. This is a good demo though. Eddy currents, let me show you the demo and then I'll explain it to you. I have here a tube. See, can't get it right and lined up. It's hollow. And then and this is aluminum. So aluminum is not ferromagnetic. I have this same magnet right here. This is a pretty strong neodymium magnet, and you'll see that it does not stick to the aluminum. Aluminum is not ferromagnetic. Now what happens if I take this, and also notice that the magnet fits with plenty of room. There's some space in there, right? Okay, so it's not going to get stuck in there. But if I take the magnet and drop it down the tube, let's see what happens. Oh, I dropped it. It didn't break. You gotta be careful with these magnets. They're very strong, so if they attract another magnet or a piece of ferromagnetic and they hit, they can crack. But it didn't crack. So in this case, what's happening? As the magnet falls, let me draw a picture. Actually, let me show you one more demo because I'm going to put this down. So you can even take this magnet if you had it, and there's no force interacting with it. But if I change the magnetic field and if I move it quickly, you can feel there is a resistive force, and that is the eddy current. When I drop it down here, it's producing a current in the tube that opposes the change in the flux, which means it pushes the magnet up, and it falls at a constant speed, and that's an eddy current. Okay, so let me put this magnet here somewhere safe. Put my tube right there, and let's draw a picture. Okay, so here's my tube. Here's my magnet. Let's say this is the north and the south. So I have this magnetic field going down, and if I take this little piece of the tube, well, I'm changing the flux through that piece of tube as the magnet moves down. That change in flux is going to make an EMF, and that's going to induce a current, and that current is actually going to go this way. It's going to go that way, which is going to make an induced magnetic field be up. So these two things oppose each other, and it makes it slow down. So moving this through there, the faster it goes, the greater this change in flux in the magnetic field. It's going to reach a constant velocity where the rate of change is equal to the induced magnetic field, but that is an eddy current. Now, the demo's cool, but it's used in a lot of other things too. If you have like a piece of metal and you need to make it slow down, you can put a magnetic field here and it passes through, and every time it passes through, it changes the flux and it produces a current that slows it down. So it's kind of useful. Okay, let's talk about, I'm not going to derive this electric generator equation. We talked about this before. I'm going to try to draw, I guess I could do it like this. Here's a coil of wire in a magnetic field, and it's going to rotate around like this. So as it rotates, the magnetic flux changes. We talked about that. Remember, flux is BA cosine theta. So as this, there's my angle right there, that's theta. If this rotates at a constant rate, then I have a change in theta. Now, how does the flux change if I change theta? It's not so easy. It's not just, you can't just divide cosine theta by delta theta, because cosine theta is not a constant function. So if you want to see how that changes, you could take the derivative. We're not going to do that because it's not a calculus-based course. But if you did that, you would find that the EMF is, what did I write? It's NAB omega sine omega t. So omega is the angular velocity of how fast this thing rotates. N is the number of loops. A is the size of the loop. B is the strength of the magnetic field. Angular velocity, and then sine of omega t, because theta changes. So you have that comes in there twice because of the derivative, which we didn't do. Again, not a calculus-based course. And that's just for a plain coil. But you'll see here that if I take a coil of wire and I rotate in a magnetic field like that, I have it, the EMF changes as a function of time because of this. So it would look like this. So this is EMF, and this is time. And you'll see what we get there, an AC circuit, right? That's what we talk about when we talk about alternating currents, alternating voltages, and that's the sine wave. So if you have just your plain DC generator like that, you get AC current out. That's why that's important. Okay. Back EMF. I guess I have to say something about this. Things are so complicated. I'm going to give you a better demo. Actually, I'll do the back EMF in another demo. I told you I'm going to make demos, and I'll do that in a different video because it's just kind of hard to see. But the short answer is that when I have an electric motor spinning, it induces. It's like a generator. When you run a current through it, it's like a generator too, so it makes a voltage going backwards. And so you actually get lower current when it spins than when it's not spinning. This is why if I have a generator for my house, I can't use it necessarily to turn on my air conditioner because the compressor, when the motor starts up, uses a lot of current, right? It uses a lot of current when it's stationary because there's no back EMF. And if you stop the motor, you get a very, very large current. That's bad because it uses a lot of current, and it can melt things too. So, okay, that was good. I got chalk on me. Transformers. Okay, this one does need another demo. And I would do this after inductance, but let's just say that I have a coil of wire. And remember, a coil of wire makes a magnetic field. And then I have a bar through here, a metal bar. And then I have another coil of wire. So this is N1. And that's N2. So there's loops around there. So what's going to happen is if I change the current here, it's going to make a change in voltage, right? I'm going to induce its own EMF because I have a change in flux, right? So I can say EMF 1 is going to be equal to N1 times the change in flux with respect to time. Now, that change in flux is going to be due to this area and the magnetic field. But we have the same area, it's the same size, and the same magnetic field because it's metal bar. So N2, EMF 2 is N2 times the same change in flux with respect to time. Now, let's call this V1, V2, and you can see that I can solve for the change in flux, delta T. It's going to be equal to V1 over N1, but this is that same change in flux, so it has to also be equal to V2 over N2. And I can solve this as V1 over V2 equals N1 over N2. So what this tells me is that I can, by changing the number of loops on the two curves, I can produce a voltage here, an input voltage here, and get a different voltage here. And that's what a transformer does. Let's see if I can demonstrate this for you. You know what? I'm not gonna, okay? Because I have to hold too many pieces to this. But here I have two coils of wire. Here's a coil with different number of turns than on this one, and I can put them in together like that. If I have a changing current here, I get a voltage across here, even though they're not connected. And that's a different voltage here than over there, and that's kind of cool. I will show you this, but not right now because I don't have any place to put it. But I will show you this. This is an actual transformer. It has extra wires in there because you can put different loops on here. But this is basically two loops. There's a loop of wire from these wires and a loop of wire from these wires. They're not touching, but they overlap so that you can have the same flux through them. And then if they have different number of turns, you can get an input voltage and the output voltage different if you have an alternating current. If they don't work with DC, okay? And you can feel the heft to this, right? This is part of what's going on those DC adapters, the older ones, the heavier ones. They have a transformer in there so they can take 120 volts from the power outlet and get to 5 volts so you can charge your phone. Newer ones are much, much smaller. They don't do this. There's another trick. It's not super important right now, but I just want you to know that is a trick. Okay. So that's your transformer equation. Oh, I should say the current is not the same, right? Isn't it? So I don't gain power. I can't gain power. So in this case, the power input should be the power output. So P1 should be P2. And they use PP and PS for primary and secondary, but it doesn't really matter. So the power is I times R, or I times V. So I have I1 V1 equals I2 V2. So let's just solve this for V2. I get V2 equals N2 over N1 V1. And if I put that in up here, I have I1 V1 equals V2. I2 V1 N2 over N1. And the V1s cancel. So I get, when I divide by I2, I get I1 over I2 equals N2 over N1. So the ratio of the currents, if I want to step up the voltage and get a higher voltage, I have to sacrifice by getting a lower current. You don't get anything for free. Inductors. Let's see what else I have on here. Okay, I'm going to explain inductors from a very conceptual standpoint. And the important thing in an inductor, I'll tell you that too. Imagine that I have a loop, a solenoid, and I have current coming in that goes like that. Well, that current makes a magnetic field, and that's fine. But now what if I change the current? If I change the current, this part of the solenoid is going to make a magnetic field that gives a flux on that part of the solenoid. So changing the current is going to induce an EMF across this thing because it's changing the flux through other parts of that. And you would think, oh, well, what if you just have one loop? It still works even if you only have one loop. And we can say that this EMF is equal to L times the rate of change of I, the current, how fast the current changes. And they put negative on here, again, because of that back EMF. So if I increase the current, then I, delta T is increasing, then this will make a voltage going that way. Essentially what this inductor wants to do is like, hey, don't change the current. I want it the way it is. I like currents the way they are. That's what an inductor does. This L is a property of the shape of that thing. We can say that the inductance, this is inductance, it has units of henries. I think this is how you spell it, henries. I'm not sure. And then if you have a solenoid like this, the inductance is mu naught, which is that magnetic coefficient, N squared, that's the number of turns, A over L. So this is the area, this is the length, and then we have the number of turns squared, and then the constant mu naught. But it depends on the properties of the thing. It doesn't depend on the current. But the key thing here is when I put an inductor in a circuit, it does not want to change the current. And this is actually a big deal. I will show you another demo for this. It's kind of a cool thing. I want to show it to you now, but I don't have it set up. That's a bummer. Well, I'll tell you about it because it's pretty awesome. Let's put that up here. EMF negative L delta I delta T. Just, I want to make a comment. I mean, this chapter is very complicated, and we're passing over it at a low level because a lot of the fundamental equations depend on things that we don't do, like calculus. So I'm just letting you know. We're kind of doing this superficially for this algebra-based course. Okay, imagine that I have a circuit like this. I really want to show you this right now, but I'm not going to. I have a battery, and then I have an inductor, and then I have a resistor. Let's put a resistor in there too. And then I have a switch. So when the switch is open, the current's zero. So let's say I1 is 0. And then when I close the switch, you would think this is EMF. I would say I2 is EMF, that's R, that's L, EMF over R, right? Because that's just that's not a resistor, that's just an inductor. But if I close the switch, I can't go instantly from I1 to I2 no matter what this is, because that would induce a voltage over here that's proportional to the rate of change. And if delta T is 0, this is infinity. And that would be an infinite voltage across that. So instead what happens is when I close the switch, the current builds up, and I get this as the current as a function of time. So that's tau is our time constant, and it's L over R. You'll remember that's a lot like the time constant for RC circuits, and that is a big deal. I will show you that at one point. So once I have it closed, eventually the current will get up to I0, which is EMF over R, and then when I open the switch, well, you can't just go to 0. This is the cool part, right? If I open the switch, you'd think it'd just go to 0 automatically, but it doesn't. Because what happens is you get a spark. The voltage gets high enough to jump the gap even though you open the switch. And that's what's called sparking. So the idea of a switch, if you have an inductor in there, when you open the switch, you're going to get a spark. Now, you can prevent that. There are ways to do that. But in a general circuit, this is something that you have to consider, especially when you have large currents, large changes in current produce large voltages, which will create a spark. Now, there is some really cool stuff that happens when you have a capacitor and an inductor in a circuit together. And I will show you that too, but right now let's not worry about that. It is pretty cool though. Okay, let's give a chapter summary of equations. I feel like I kind of rushed through stuff even though I didn't. So the first thing is Faraday's law, EMF negative in d phi dt, where phi is the magnetic flux, B a cosine theta. That's the most important thing. These two equations are the most important thing. And the idea that a changing magnetic flux creates a voltage. Then we also have this EMF is BLV. That's that motional EMF. We derived it two ways. Then we have this V1 over V2 equals N1 over N2 for transformers. Transformers are important. I'll do some calculations with that later. Oh, I didn't do this. So if we have an inductor, then if we have a current going through it, we can actually store energy in the inductor just like we can store energy in a capacitor. So the energy in an inductor, E, what did I use? I guess E, 1/2 Li squared. So that's the inductance and that's the current. And it looks a lot like, remember this, 1/2 CV squared. That's the energy stored in a capacitor. They look a lot alike. And then finally we have this for charging or turning on a circuit, I0 1 minus e to the negative t over tau, where tau is L over R. And then when you open a circuit, it looks like this, I0 e to the negative t over tau. Okay, so that's chapter 23, electromagnetic induction. And I will make a demo video, I promise. There we go. Okay, the end.